In this example, we follow this four-step procedure to determine the entire interval of convergence of the given power series. Now, the idea here is if you notice that a sub n is a function of x. So there are certain values of x that will cause this series to converge and certain values that will cause it to diverge. Every power series will converge for at least one value. For example, if you were to let x equal 0, then you would end up with the summation of 0 from n equal 1 to infinity, which equals 0, which converges. Pick different values of x and you will see that you get divergence. So we want to find the complete set of values of x that will make this series convergent. So we begin by first finding an expression for L, which is defined to be the limit of the absolute value of a sub n plus 1 over a sub n. Find an expression for L in terms of x. This is the beginning of the ratio test as we saw in the last example. So let's begin by writing L equals the limit as n increases without bound of the expression. As we did before, computationally it's a lot easier to do the absolute value of a sub n plus 1 times the reciprocal of a sub n. So let's go in there. Everywhere we see n in a sub n, let's replace that n with n plus 1. So we end up with x to the n plus 1 over n plus 1 squared times 3 to the n plus 1. Let's extend the fraction bar a little bit. Times the reciprocal of a sub n, which will be n squared, 3 to the n over x to the n. And of course, we want to take the limit of the absolute value of that expression. Now, we notice that there's certain cancellations that are going to take place here between the powers of x and the powers of 3. And you can supply the details there. You'll see that you end up with x in the numerator. There's an n squared in the numerator. In the denominator, we have an n plus 1 squared, and then there's also a factor of 3. Now, several things here. We'll take them one at a time. Notice that the n squared, the n plus 1 quantity squared, and the 3 are all positive. The only quantity that can possibly be negative is x. So the x stays inside the absolute value bars, within the absolute value bars. There's a 3. Then we have an n squared over the quantity n plus 1 squared. Again, we're taking the limit as n increases without bound. So let me erase this here. Since we're taking the limit as n increases without bound, that means that the absolute value of x and the 3 can be slid outside of the limit because they're constants as far as this limit is concerned. And of course, as n increases without bound, you can show this using the L'Hopital's rule, that the limit of n squared over n plus 1 quantity squared as n increases without bound is the limit of this is 1. Sorry, should be a 1 right there. So we end up with the absolute value of x over 3 for our value for L in terms of x. Now part B, it says, now we want to solve the inequality L less than 1. Why do we want L to be strictly less than 1? Those are the conditions that guarantee convergence of a series using the ratio test. So we start here with L less than 1. The expression for L is the absolute value of x over 3 less than 1. We multiply both sides by 3, and you get that the absolute value of x is less than 3. Or another way of expressing this absolute value inequality is negative 3 strictly less than x less than 3. So now we have an interval to work with. Now I'm just going to point out that the 3 here, that is the right endpoint of our interval, and the negative 3 is the left endpoint. So what we have to do now, notice that if x were equal to 3 or x equals negative 3, then this expression, if you go back and look over here at this inequality, if you were to put 3 in for x, the absolute value of 3 is 3. You get 3 over 3, which equals 1. So the limit L would be 1, which we know that the ratio test is inconclusive when L equals 1. So we have to test the endpoints individually. So I will start with the right endpoint. For the right endpoint, I'm going to let x equal 3. And I'm going to place 3 in for x into the original series. Doing that gives the following. Summation of 3 to the n over n squared times 3 to the n. Notice that now a nice cancellation takes place. The 3 to the n's cancel out. So we're left with the following series. 1 over the series of 1 over n squared, which converges. And how do I know that converges? Well, it's a p-series with p equal to 2. And the significance there being that this number is greater than 1. So we're guaranteed convergence there. Now, that's the right endpoint. Now we go to the left endpoint. The left endpoint is x equal negative 3. So now I let x equal negative 3 into the original series. So the series now looks like this. Negative 3 to the n over n squared, 3 to the n. Again, cancellations take place. However, when I do my cancellations here, the numerator can be written as negative 1 to the n times 3 to the n. So the 3 to the n cancels with the 3 to the n in the denominator, and we're left with the following series. Negative 1 raised to the n power over n squared. This is an alternating series. If you take the limit of the absolute value of a sub n as n increases without bound, you will get 0. So it converges. So this series converges at both of the endpoints, so we state our interval of convergence as any value for x within the closed interval negative 3 to 3 will guarantee convergence of the original series.